All right, yes, indeed, this is the right link. Sorry, I'm a couple of minutes late there. Um, can folks hear me out there? Can I get a quick mic check? Let me stop the music. Okay, Google, stop. Boom, boom, boom. I hope everything's good. All right. All right, so in this lecture, bubble sort, insertion, the selection sort, counting sort will be featured. There are some really weird sorts out there. That's from one of our staff. Thank you, staff. So before we get to sorting, we kind of need to finish up union find, which we didn't get to last time. Um, that's okay. I think if we cover the first half of elementary sorts, specifically bubble sort, maybe we'll get to selection sort. That's completely fine. We should still make the schedule before the exam. All right, but let's get started. Basically, this slide is kind of where we left it off last time, which is an implementation of set union using ranges. Okay, by ranges we mean pairs of iterators, right? That tell you a begin and an end to a specific range. So we were talking about merging two subsets, right? Set 1 and set 2. So therefore we need 4 iterators there to represent the range from the first set, then the range from the second set, and then an additional iterator as the output iterator, and then a comparator, right? Which, if you started project 2, you're very familiar with right now. Okay, implementing your own comparators using functors. And so this code basically goes over the example that I went over last time. It's just code that execute the example quite nicely. So I'll let you kind of look through the code to play around with it. It's interesting, generalized templated code. But if you recall, it basically has pointers, well, in this case, iterators, right? The begin iterator for, or the start iterator for set 1, and then the start iterator for set 2, and then you move them along as you push into the output set, which is basically setting the output iterator. And so you need to move the pointers along based on what you end up outputting. So, all right, go back to this example and check it out. And here's a summary of implementing subset using ranges. So, if we were to implement a bunch of operations using ranges, as we showed in the previous slide, you'd have an initialization, which would be, well, if you don't really care about sorting, then initializing something like that is basically constant time. You're given the range. You don't really need to do much. But if it's looking to maintain some sort of constraint, like we saw in the last lecture, then it's something like n log n time. Clearing, that's going to be constant time if if the range for the container was declared in the stack, so it lives in the stack. It's constant time. But if it's contains objects that live in the heap, then that can take linear time because you have to go over each one of the elements and call the constructor. Is member, if by binary search, right, which is is member is analogous to find, lookup, search, whatever you want to call it. That's log n time by binary search. Copying is linear time if you want to copy everything. Set union is linear time by the previous algorithm that we saw. Basically it's linear, where n is really the sum of the size of set 1 and set 2, okay, of the elements in set 1 and set 2. And then set intersections we haven't discussed in detail, but similarly is also linear in the size of the input sets. Okay? All right, so we also have in the slide a job interview problem that I will skip in the interest of time. It's actually quite interesting. It does come up often in interviews as far as our experience goes, but so don't get too hung up on it being like an interview problem. just look at it as a challenging problem that you can think about, brainstorm, and try to come up with a solution. And then come to office hours, and we can discuss in details. Okay. Excuse me, I have my son interrupting my lecture. Get out. Thank you. Sorry. Apologize for that. All right. So on with specifically union find. Okay, this is a rather interesting operation for which we really haven't given you a problem to apply it to yet. We will later on the semester, which is why we're discussing it now. Okay, and you will implement it in lab. Okay, you will implement union find in lab, specifically one of the more performing variants of union find. Union find is the context in which you will see it in this course, is in context of graphs, right? So when you have nodes and you have edges. But more generally, what you're looking to do is represent a bunch of disjoint sets. Okay, so every node in some graph can start out as being its own set. Okay, and then as your graph algorithm goes along, it might start to increase the size of the set by joining other smaller sets, well, not necessarily smaller, but other sets with other sets. So basically merge them together. Let's say that, particular application would be if you have the Mars rover and there's a bunch of like peaks in Mars and you're trying to diverge them. So maybe the nodes are the peaks and maybe the edges are kind of whether the rover was able to find a path from one peak to the other, right? And so let's say the rover was able to find, I guess a cluster of peaks that it can get to, like Alba, Patera, and Tempe, and whatever. So those are connected by red edges, and then there might be another cluster that's connected by blue edges there on the slide, and then yet another cluster connected by green edges, right? And then all the other ones that don't have edges can just be maybe independent peaks that the rover was not able to get to, right? So they're not connected. Okay, so there's a bunch of disjointed sets here, right? There is kind of the red subset, which contains what? 1, 2, 3, 4, 5 peaks. Then the blue one has 3 peaks. The green one has, 6. And then all the other ones that are white are just disjoint sets that just contain a single element, right? So that's the representation that we're looking to implement, meaning we have these disjointed sets and something might be happening. In the example, it was the Mars rover trying to get to the different peaks. And as the algorithm moves along, you want to increase the size of the set, right? Because all of a sudden you've found another node that shares an edge with one of the nodes that's already in the set. So that set would grow to incorporate that new node that it has connectivity to. Okay, so the numbers on there are really just labels, integer labels for each one of the nodes. Because again, we keep using integers because they're simple to use. Okay, so like I said, you have the red subset, the blue subset, the green one, and then a bunch of single element sets. Okay, and usually with these algorithms, like we won't go over it in detail yet. We will get to that after the exam. But usually you start out with everything being, a single element set. Okay, and as the algorithm goes along, it basically ends up having all the nodes or all the elements in the same set, right? So you want to get to a point where everything's single element set to just having one set that has all the elements or nodes in it. Okay. All right. So the two operations that we need to achieve this are find, which is lookups, so fast lookups, and union, which is how do I take two particular sets and join them together, which we discussed earlier for specifically sorted ranges. So, oops, did I go back? So find is check if the element belongs. Union is merge two sets together into a single set. Okay, and so this is why we kind of call this union find, right? So notice that we're leaving intersection out of it. We're not going to discuss intersection or anything like that. All we care about is union find, because this is what's going to be relevant for algorithms later in the course. Okay, so let's look at a quick example. So let's say you have a set of items right here. Again, we're going to think of them as integers. They're all a different color because they're single element sets. And here, I mean, the better label here is just set one rather than group, just to avoid the mathematical distinction. So this is set. So set one might be 1, 4, 5, 8, 10, and then set 2 then might be incorporated as 2, 6, and 7, right? So we're just choosing that as an example. So admittedly, if they belong to the same set, then maybe we would change all the colors. It's not shown here in the slide, but if I'm going to group them together belonging to the same set, then I would potentially then change all the colors. So the question would be, are 1 and 8 connected, right? Are they in the same set? Okay. And so furthermore, so this would be a question that find will answer, right? And then the other thing that we would want to do is, in the case that, say, 1 and 6, for example, have some connection. Right? And here connection is in the most abstract sense, right? It's really context dependent on what we mean by collection. Again, the previous example was peaks in Mars that have a path to each other. What do we do, and how long does it take to merge the two sets, right? So if I find that a 1 and 6 share an edge, then that means that now set 1 and set 2 need to belong to the same set. Okay, so what is the fastest way that I can merge them together? Okay, and that's what we're going to be looking at next. Algorithms to perform these two operations. So from what we've described so far, it would be that union takes linear time, okay? Because in the worst case, I have to create, say, some additional container that fits both set 1 and set 2, and then copy everything from set 1 and set 2 into, like, similar to what we did it for the sorted ranges set union algorithm. Okay, and then the find algorithm, okay, not being any particularly smart about it, would be linear time, right? Because you'd have, if you have a set, and again, it's set in the most general sense so far, you would have to invest linear time to find whether a particular element is in there. And you might say, like, well, what if we, maintain sorted ranges? Then that'd be log n time. True, yes, but we're actually going to describe better algorithms that will eventually get to algorithms that run better than log n time. And we don't have to worry about maintaining the sets in sorted order all the time. Okay? All right, so let's look at these data structures. What we would want to do is basically maintain representatives for each one of the elements, okay, or the nodes. Kind of depends on the context that you're talking about. I'll stick to call them elements. Okay. So every set element K must know its representative J, whatever that is. Okay. And so if each element keeps track of its own representative for kind of which set it belongs to, then the find operation is quite fast, right? Because I just need to check, hey, what's the representative of K and what's the representative of J? Okay. And if their representatives match, then that means that they belong to the same set. And if they don't match, they're not in the same set. Okay. All right, so let's look at how this would work. So we have, say, a bunch of items. Again, we're keeping it simple. These are just integers. And so, and then each one is going to have their own representative. And what we're going to do is everybody's going to start, because they're, again, everything start out as being single element disjointed sets. So everyone will have their own representative right here. Okay. So right now, if I were to check, oh, are 2 and 3 in the same set, right? I would query the representative of 2 to just see that it's its own representative, which means that, you know, it's its own set. It's a single element disjointed set. And then I would do the same with 3, okay? And then compare that the representative for 2 is 2 and the representative for 3 is 3. They're different representatives, so therefore they're not in the same set, okay? All right, so now let's go over a bunch of operations on the right-hand side of the slide here, okay? Join here, and I'm going to note it up here. Join here means that I'm doing first a find followed by a union. That's what we mean by join here, and I apologize for the handwriting. Okay, so that's what we mean by join down here in this operation, right? So let's go over a quick example of this. So in the first operation here, where we're trying to join 1 and 3, that would mean that I would do a find on 1 that would just tell me that the representative is 1, right up here, okay? And then also do a find on, what is it, 3, and that tells me that its representative is 3, okay? So after that, we would do union of 1 and 3, which means that what I would do, and this is by convention, okay? So I'm making the assumption that this is what I'm going to do, because actually there's multiple ways of implementing this. Like, for example, oh, if I need to pick a representative, it's going to be the one that has the lowest integer value, okay? That could be an option. But here, we're just going to say whatever is the left element that I'm joining, that's going to be the representative, or I'm going to pick that as a representative. So that would mean that now the representative of 3 is going to be, going to set it equal to 1, right? So up here, it would mean that this is the change that I have after the join, the first join. Okay, it means I've updated the representative of 3 to be 1. Cool? All right, so that's easy enough. In fact, and for the later, I'm going to erase some of this to make some space. And for the later operations, they're very similar, right? So now I'm looking to join 3 and 8. So if I do find on 3, by the last update, that gives me a 1, okay? Because that's the new representative. And then I do a find on 8, that gives me 8. So that means that union of 3 and 8 implies that I'm going to update find on 8 to be 1. Okay. And now you can see that so far we have, in the same set, we have 1, 3, and 8. They belong to the same set. Everything else is its own single element disjointed set. Okay. All right, I'm going to make some space here. Third operation, join 1 and 5. Similar situation. The representative of 5 now, that's supposed to be a 1. Let me write that again. So I won't write that one out because it's a mirror of what we've done earlier. And so now we have join of 7 and 4. Okay, they're disjointed. I want to connect. I'm going to add. I want to union them into their own set. By convention, because we've chosen to, I would pick 7 to be the representative. Okay, so that means that for 4, the representative is now 7. Okay, and then join of 7 and 2, I would do a find on 7 to see its own representative, a find on 2 to see that its own representative, and by convention, I would pick 7, again, the first argument to the join, that's what I'm going to pick to be the representative. All right, and lastly, this last operation is going to be a join on 2 and 5. So let's write this one out. It would be a find on 2. That gives me 7. Okay. Then a find on 5. That gives me 1. Okay. And what would happen now is like, oh, well, I now have to take, when I do the union of 2 and 5, I now have to take every element that belongs to the set with representative 1. I'm going to need to change all those representatives to now be 7. Okay, so all the updates here, all the updates earlier were just simple, but now this update is going to be quite large, right? I'm going to have to take the representative 1 and set it to 7, the representative 3, because the 2 is already 7, so on and so forth, all the way to the representative 8 that I will set to 7, right? So everything now 7, 7, I think except for 6, right? Because we haven't really done anything with 6. So at the end, I've joined together or union all the nodes except for 6. Because if you look at the join operations, I never did anything with 6. Okay? So if you notice in all this example, the find was fairly fast, right? I just needed to look up the representative. That's it. It's basically a constant time lookup. But the union could potentially take a long time, because if you saw with the last operation, I had to update the representatives for a bunch of elements, right? If the set grows large enough and then I need to update all the representatives for that large set, then that's a lot of updates that need to be done. In fact, in the worst case, it'd be linear time, which is what's shown now on the slide. Let me erase some of this stuff. Okay, find is constant time. Okay, but then union is going to be linear time. Okay, so that's kind of our first algorithm for union find that uses representatives. So far, so good. Okay, but can we do better? Okay, well, we can do better even with this approach. That is, if we were to keep track of the sizes of the sets, and then say like, oh, if the size, if I'm going to do updates of the representative, I might as well only update for the sets that are smaller, right? But then you have to keep track of the sizes of the sets, which is also pretty annoying, and it can lead you into bugs. Okay, so can we do better than this? Is there a better way to do this? Okay, largely because we would want to avoid doing or investing linear time to do a union. Okay. All right, so let's do a smarter union find. In this case, what we're going to do is not necessarily store the actual representative for each element. Okay. But instead, just make sure that I can find the representative quickly. Okay. So that means that when I do a union, I don't have to invest my time updating a bunch of representatives, but then I kind of shift the burden to find, because now we have to spend more time during the find function to actually find the representative, because I have to basically traverse back through representatives to find what the parent representative is, if you will. All right, let's look at an example of this. Okay. So the first few joins here are going to look quite similar. Let me write out 1, 2, 3, 4, 5, 6, 7, 8. The joins here, the first few ones are going to look quite similar to the previous approach, right? Joining 1 and 6 means that now 1 is a representative for 6. Join 1 and 8 means this is a representative. Then 1 and 3 means 1 is the representative. Now 6 and 5, let's write this one out. So if I did find on 6, that gives me that the representative is 1. Okay. In fact, notice that really here, if I were to write out the traversal to find the representative, it would actually look like this, right? It would tell me find of 6 leads me to find of 1, which gives me 1. Okay, and that's how I would know that the representative is 1, right? Because 1 was its own representative, so I have, nowhere to look up further. So that's when I say, okay, so the representative of 6 is actually 1, right? So in short, boom. Oops. I'm going to write this as 1. And then find on 5 gives me 5. So that means that if I do a union of 6 and 5, that would mean that my update should be that the find on 5 should be 1 now. Oops, that's supposed to be a 1. All right, so I did this here. All right, now join of 4 and 7. This one's fairly straightforward like before, right? Except we would pick this we would pick 4 to be the representative of 7. Then join 4 and 2. We would pick 4 to be the representative of 2. Again, that's by the left operand convention for the join. And then lastly, joining of 5 and 4. So we'd have a find on 5, right? That gives me 1. Then a find on 4. That gives me 4. Okay? But notice, let's spell out what the find on 5 would be. The find on 5 would be that it goes to 6 and then it goes to 1. Right? So spelling it out here. Because of the join number 4 that I have right here, that would mean that strictly speaking, this would do find on 5, find on 6, which then gives me find on 1, and then eventually gets to 1. Okay? And then the union here would be, of 5 and 4 would just be, I make sure to set f of 4 to be 1. Okay? Equals to 1. And then if I were to check which elements belong to what, right? I would check, well, let's see, what element 1, it's in a set labeled with 1, okay? Element 2 is in a set that's labeled by 4, but I have to follow all the way through. And if I go to 4, then it tells me that the actual set where it's at is 1. Okay? So that means that 2 is also in set 1. Then similarly for 3, it already tells me it's set 1. 4, it already tells me it's set 1. 5 already tells me it's set 1. 6 already tells me it's set 1. 7 tells me I have to go to 4. 4 tells me that it's in set 1. And then 8, it's already telling me it's set 1. So basically this example ran all the way through to merge all the elements into a single set, right? And if you look at the joins, then it makes sense. Okay? Cool. So that's the second example. Here that was a kind of smarter approach than what we had before. Again, what we did is shifted towards, instead of always updating the representative when you're doing a union, you basically do no updates during the union other than the elements that you're looking to join, right? Or union. But then that means that find has to invest more work to find the actual representative for that element, right? Because the representative that it has might not necessarily be the ultimate, or call it root representative for the set, right? It has to traverse back representatives until it finds the representative that has itself as its own representative, which was the example that we had when we did join number 4, okay, with join on 6 and 5. Okay. And so that means that now union is constant time, right? Union means I would only do 2 updates to change the representative of the two arguments that the union operation would have. Okay? But then find might be linear time, right? You might have to traverse back through all the representatives in order to find the ultimate root representative. So basically, we shifted the burden from union, that was linear time before, to find, which is now linear time, but now union is fast. Okay? So, how about if we come up with something that gives us the best of both worlds, right? Meaning a fast union and also a fast find. Okay? And the answer to that is called path compression. Now, this is what you were actually going to end up implementing in lab. Okay? The trick to path compression is the fact that so far we've been talking about the find operation as being read-only. Okay? So I just look up whatever the representative is, but it doesn't update anything. Okay? We're going to change that. So now union will be able to make updates to the representatives as I traverse along the representatives to find the ultimate root representative. Okay? And that's what's actually going to get us, as you'll see, to a very fast both union and also find operations. Okay? And specifically because even though we are shifting the burden to find a bit by having it do some updates of the representative, and I'll show you in the example what that means. Okay, we are also going to be able to amortize that operation over the lifetime of the union find algorithm, and it's going to end up that both operations are going to be amortized constant time, just to save you the suspense. Okay. But we're actually not going to show you mathematically why it leads to that. We're just going to hand wave and tell you that it does, right? But it's you know, if you understand amortized complexity, then it's interesting to see, right? So again, we're basically going to amortize any of the union find steps. We're going to amortize over the lifetime of those operations. And that by lifetime here, I mean, again, remember, you start all single element disjoints and end with a single set that has all the elements, right? So the lifetime is the starting of all elements being independent and the end time being all elements are interconnected in a single set. Okay, so that's the lifetime. Okay, and we won't go over the analysis of that, but just know that there is some rather surprising results that this, if you do that amortization, it means that it grows really, really slowly, right? In fact, it is bounded by the inverse Ackermann function. So that means, and I think that value is roughly around 5. So it basically means that your union find, right? So this is, I think that's 5, but don't quote me on it. Just the point is, it's a constant. And so basically it's just asymptotically going to tend towards 5 and never get above 5. Okay, so this is this means that every single either union or find operation is going to be roughly constant time. Okay. All right. So let's look at how this would work, and then we'll take some time to answer some questions on the chat. We also need to start with our representatives, right? Join of 2 and 4, right? That would mean that the representative for 4 is now 2. Join of 1 and 2, that would mean that the representative for 2 is now 1. Okay. Join of 5 and 7, that means, right, so I'm done this one. Join of 5 and 7 means that now 5, okay, makes sense, is the representative for 7. Then join of 5 and 6 now means that 5 represents 6. Join of 8 and 5 means now that 8 represents, okay? 5. All right, so far, all these EC operations, I haven't really shown what path compression does, okay? What path compression will do is that as it traverses back to find the ultimate, call it ultimate representative for a set, it's also gonna update the representatives that it saw while it was traversing to be that representative, right? So that next time you call a find, you'll basically have the freshest, most up-to-date version of the representative for all the nodes in the set, right? Or all the elements in the set. Okay. So what would happen here, right, is that if I call find on 4, that gives me find on 4 gives me, and I'm going to spell it out. Just gives me find on 2, which gives me 1. Okay. And just right there, when I did the find, and I noticed that I had to go through 2 to find 1, the find operation itself is going to say like, all right, so as I'm done with this operation, just before I'm finished with it, I'm going to update directly. Oops, I draw it the wrong place. I'm going to update immediately the representative of 4 to be 1, right? So immediately right there, as I did that first find, I made it 1. And what that's going to do is that next time I do find on 4, I won't have to go through 2 to find the actual representative. It would have already been updated, right, by the find operation. All right, so now we would do a find on, what is it, 7. That basically tells me that I need to go through, where is 7? Oh, I need to go through 5, okay? Which then tells me I have to go through 8, and 8 is its own representative, so boom, I've found the ultimate representative, okay? And similarly, what I would do right there, right? I haven't even called union yet. I'm still doing finds, right? Find would make sure to update 7 immediately to make its representative 8. Okay? And that's when find operations would be done. And then the union is kept simple, right? I can just do union of 4 and 7 and 4 and 7, and like before, I would say, okay, now the representative of 7 is just going to be 4. Okay? Oh, sorry, not 4, but 1, because I made that update in the previous find, right? So it would just be 1. Okay, so here it would be that I set the representative of 7 to be equal to whatever the representative of 4 is, which by this first operation right here should be 1. Okay? So again, the key, and these are subtle differences which, you know, if you're watching this in 2 times speed, and I know I talk fast, so you might want to put it at regular or even slow it down. So we go step by step, and you can see the differences between the previous 2 examples, okay? Specifically this one, we were updating the representative. As the find operation was finding the representative, the ultimate representative, it was updating the representative all along, all right, for each one of the elements that were in that set that I had to traverse. Okay? And that means that next time I do a find, I won't have to incur that many steps to find a representative. So that's why you're amortizing the operation, because if you do these updates, then on average, your amortization, your number of steps that you would do for the find operation and also the union operation is going to be in the order of this Ackermann function, which, as I said, is bounded above by a constant. Okay, so that means that they are amortized constant time. So I'll delete all this so you can see. Okay. All right, cool. So let me break a second. See, we do have folks from staff on the chat. That is great. There are a variety of ways. Yes, that is a comment. There's actually multiple ways of implementing union find. Okay, that's what I said. Like, there are conventions that say that if I'm going to union, the one that I'm going to pick as a representative is whatever integer is lower, integer value for the representative, right? Assuming that the representative is an integer, because you can totally have representatives that are not integers. Nothing in what I've described means that they have to be integers, but it's just easier to think about if they are integers. Okay. We also spoke about there being like, I keep track of the size of the set. There's implementations that are like that, but path compression is really the most efficient way to implement it. It is trickier and it can lead to bugs because of the updating for the find operation, but it's still doable. In fact, that's what you're going to do in your labs. Okay. All right. Yep, correct. That's basically what we've been working along. You have some item that we're labeling with integers, and then representatives that we're also labeling with integers, right? You can think of this behind the scenes as being an array, right? And yeah, your array can start indexing at 1 here, and then forget about the 0th element like we did for heap. You can think of it that way, right? All right, so let's move along. That's basically it for union find. More on it when you get to labs. We do have a whole bunch of interesting study questions for you to look at. Make sure to do that. They're study questions for a reason, right? They're good practice for exams and such. Okay, so now let me bring up the lecture on elementary sorts. Excuse me. All right, elementary sorting methods. Okay, so this is, you've definitely seen sorting methods before. You've probably seen implementations of sorting algorithms. Hopefully everyone has, made a call to a sorting algorithm before, whether it be STL or some other language. So you've used sorting algorithms in one form or another. Even in daily life, you would use sorting. Okay. So what we'll do is we're going to actually discuss elementary sorts, and they're going to be called elementary sorts because they're not the most efficient sorts. But they are useful for studying how one can look at an algorithm and basically find ways of improving the algorithm. Right? Now, most of the things that we will discuss are going to look like kind of micro optimizations to the algorithm, which is true. But the idea is for you to look at the example of taking some algorithm and thinking about what it does and where things the algorithm can be doing things better. Okay. And of course, we could try to come up with some really fancy algorithm to do this with, but then you have kind of to think about what the algorithm actually does and what is it, what's the data and what, so rather than pick something really complex to analyze and to improve, let's pick something that's very familiar with and that people use often in practice, which is just sorting algorithms, right? And so for elementary sorts, basically, that's your bubble sort, which you probably heard of before, selection sort, insertion sort, and counting sort. Probably today, we're going to cover bubble sort and selection sort, and we'll start on Tuesday with selection sort and counting sort. I mean, it depends how far we get in the slides. Okay. Now, similar to how we were discussing heaps, we said like, hey, really, you know, what you're using to store, what you're storing in your heap can be any type of object as long as they're comparable. We just chose to use integers because that's easy for, teaching purposes. Same thing with sorting, right? As long as you can compare them, you can compare any type of object. It doesn't just have to be integers, but for the most part in these slides, it's just going to be integers. Okay, but it could be any key as long as you provide a functor to compare the objects. Now then we have the category of high performance sorts. It's kind of a fancy word. Also known as efficient sorts. High performance has, I don't know, way too many connotations there. So I would just call them efficient sorts. And that's your quick sort, which is a very interesting algorithm. Merge sort. And lo and behold, there's heap sort, which we've already covered, right? So if you go back to the heap sort lecture, we talked about the fact that heap sort is an efficient algorithm. All these sorts, as we're going to see, are going to be n log n algorithms, whereas these over here are all going to be O of n squared. Okay. Then there's also radix sort, which we will not discuss, but encourage you to look up. It's a very interesting algorithm for sorting. All right, so let's get on with elementary sorts. But one thing to note is that elementary does not mean that these sorts are useless. And in fact, we're going to discuss situations in which sometimes even an elementary sort might work better than one of the efficient sorts. Okay, and in fact, sometimes there might be situations in which you don't want to rely at all on an efficient sort, because even though they might be fast, they would end up doing more work than an elementary sort. And we'll discuss how that can come about. So the idea is to, illustrate how to approach a problem. This is what I was alluding to earlier, how to compare multiple solutions and how to optimize, okay? So we will, for the most part, be talking about arrays, okay? Specifically in this lecture. And then we're some of these algorithms are easy to adapt to a linked list. Some of them are not as easy to adapt to a linked list. We won't cover the details, but we will ask you questions to think about, right? Like, from what you know about, say, bubble sort, how would this behave if instead of an array, it was a linked list, right? And then there's the sorting algorithms. It's actually not plural, it's just mainly one, for which it's specifically suited if you have linked lists, if you're trying to sort a linked list. Save you the suspense, it's merge sort. We're going to have a dedicated lecture on merge sort, which is the sorting algorithm that is best suited for linked lists. Okay. All right. So for the STL, if you haven't used it before, what we would need to do is pound include algorithm. Okay. Then you can declare a vector or an array for that matter, and then pass it to the STL sort function, which is in the std namespace, just like everything STL. If you recall, this begin A is syntactic sugar. You could just as well call it with sort. What is it? A dot begin. A dot end. Well, hopefully that makes some sense. All right, so we will use indices and array, right? So we're not going to be using pointers, although indices we're also going to refer to as pointers because that's what they do. Like an index just points to some specific slot in the array. So we will use those names interchangeably. And for the most part, just using arrays, okay? So one good exercise that, if you choose to accept the challenge, is to rewrite a bunch of the algorithms that we give you here using iterators, okay, rather than indices, okay? All right, so before we dig in to the details of the algorithms, let's get over some nomenclature here. When we say internal sort, okay, it means that your sorting algorithm, I mean, basically your sorting function, if you will, right? But the function implements an algorithm. It can see all the elements, meaning all the elements, they fit in memory. You can load your array in memory. All your data, you just load it in memory. Okay. In fact, all the examples in this lecture are going to assume that it's a type of internal sort. Okay, because all we're sorting are integers. Integers are very easy to fit in memory. So even if it's a very large number of them, so your algorithm will have all the data available to do the sort. Okay. Also, we assume by way of the fact that we're using arrays that we have constant time random access. Okay. Now then there's indirect sort, okay, which means I might not be able to fit all my actual data in memory, but I can fit like some indices that are keys to identifying the data that might live somewhere else. Okay, so if I sort and reorder the indices, that's just as good as sorting the data. Okay, so you would need some prep work, right, to identify the correct indices for your data that represents your data as you need it to in order to compare two different sets of data just using the indices. Okay, and then that way your algorithm really only cares about these indices. As long as that setup is done correctly, your algorithm, your indirect sort, will only care about those indices. And then there are external sorts, okay, where really I can't fit anything in memory. I have to rely on disk. Okay, and you might be like, oh my God, when would that happen? Actually, nowadays this happens quite often, right? And this is my first shout out to 403 students. This is when I would interject with some sort of big data stuff, right? Oftentimes, if you're doing big data, which you're talking terabytes and terabytes of data, and you need to sort that data, you can't, if you're going to buy a computer that has, terabytes of RAM, that would run you a pretty penny. But then if you just have a cluster of smaller machines, that is way cheaper. And then how would I go about sorting all this data that lives in a bunch of different machines? Okay, it's a very interesting question that will, when we get to merge sort, we'll see how it could be done. Okay. But if you're talking about a single machine that still doesn't have enough memory, what you can do is just load up chunks of the data that you're looking to sort, right? And sort that sequentially. Of course, there's a step afterwards that you would need to do, because the fact is, if you have a bunch of sorted chunks, that doesn't mean that together they're going to be sorted. But think about if you have two sorted sets, you already know an algorithm to union the two sorted sets. Okay, so then that's what you would need to apply after you sorted the different chunks. And that algorithm is basically the previous lecture where we talked about merging two sorted ranges, or union two sorted ranges. All right, so a nice exercise that we sometimes do in lecture is to just implement a swap function. Interest of time, we'll just give you solution right there. Fairly easy. I mean, you need to have somewhere to store at least one of the objects that you're looking to swap. So this example is just using integers, but then the example below is using a template, so it could be of any type of object. Okay, and so that's fairly. You've probably written something like this before, but ideally you would rather use the swap that is included in STL, right? By doing pound include utility. Okay, it already gives you a swap function, and that is way better to use because it relies on the move semantics that are available as of C++. What I forget which one it is. 1Z. I don't. So just make note of that. Okay. All right. So as we analyze these algorithms, what is it that we're looking for? Okay. Well, obviously we care about asymptotic complexity. Okay. And to save you the suspense, all these algorithms, the asymptotic complexity is, on the worst case is O of n squared. That's why we're calling them elementary sorts. Okay. But with sorting, because we want to consider different kinds of inputs to the sort, right? We might want to consider what happens with this algorithm in the average case, right? So not just the worst case, but the average case. And also to save you the suspense, for elementary sorts, the average cases, for the most part, in runtime, is still going to be O of n squared. But there's still interesting situations that arise when you consider different kinds of input to the sorting algorithm. Okay. Furthermore, we care about whether it is a sort in place, which just means that you basically reuse the same array that you're given as input to do the sorting. You don't rely on an additional O of n sized array to do the sorting. Okay. So that's what. So if you have to create, say, call it an output array, then you're basically incurring O of n space in your algorithm, which means that it's not a sort in place. It's a sort out of place. Okay. Then there is the fact that when we get to recursion, which we won't for the elementary sorts, but we will for the efficient sorts. When we do recursion, we need to consider what happens with the stack, right? And if you recall from your 280, right, there's tail recursion. If it's tail recursion, then we're all in good. But what happens if, the algorithm cannot use tail recursion? Okay, and we'll see examples of that. Sorting in place, but have pointers or indices, right? It basically comes from what I was mentioning earlier about indirect sort. And then we'll see an example specifically of a sort that uses omega extra memory, meaning the algorithm doesn't work unless you use extra space. Okay, that's, again, saving the suspense. That's going to be merge sort. You might be like, oh, well, then why is merge sort so good? Well, we'll talk about that later. But yeah, merge sort, in fact, well, let me rephrase that, because there are ways to implement merge sort that does not use extra space, but it's so convoluted, so hard to do, people don't do it, right? And plus, for the specific cases that you want to use merge sort, it is considered okay to invest that extra memory. Okay. So the omega tells me that I at least need extra memory that's in the order of n. Okay. So additional desired qualities would be stability. Okay. So stability basically means that if you're looking to sort two things that have the same key, okay, and you pass and they come out, let's look at this by example, right? Because I have an example and this is much better to see. It's actually not a hard concept, but it's easier to see by an example. Let's say that we're looking to sort these names right here, okay? And we want to sort by last name. So our key here, so each string is a first name and a last name, but the key that we're using to sort is by last name. So the key is the last name. So we see that both Charlie Sheen and Martin Sheen have the same last name. Okay, so in our sorting, they would be considered, same key, right? So if they come out sorted, we know that our sorting algorithm are going to place them both next to each other because they have equal keys. But stability would mean that even if you place them next to each other, they should come out in the same order that they were given as input, right? So an example of a stable output would be that because in the input Charlie Sheen came before Martin Sheen, that's the same order in which you will see it in the output when you sort it. But then an example of an unstable sort would mean that there is a chance that Martin Sheen comes before Charlie Sheen. Okay? So, if the algorithm does not guarantee the first case, then it's considered to be an unstable sorting algorithm. Okay? Does that make sense? Well, I guess I can't. I kind of ask that usually in lecture, but it's hard to kind of gather feedback while doing these YouTube lectures. All right. So types of sorting algorithm, and we're often going to see this. There's a non-adaptive sort, which it means that it doesn't take advantage of a potential state of the input array. Okay? So basically, all the sequence of operations is independent of the order of the data. Okay? Conversely, an adaptive sort might be able to perform better if the input array is, call it, somewhat sorted. Okay? So, it's not necessarily that it's somewhat sorted, is that it performs different sequences of operations depending on outcomes of comparisons, right? And one of the examples that we'll show is, hey, would this algorithm behave better if the input array is somewhat sorted? And again, I'm hand waving that right now. What do we mean by somewhat? But we'll definitely describe that in more detail in the next couple of slides. And then we have worst case versus best case. And here is one of the examples where actually thinking about a best case of an algorithm is quite useful, right? For most algorithms, when you analyze base case, it doesn't really give you much information about the algorithm or its behavior. But it turns out that for sorting algorithms, specifically elementary sorts, considering, well, not necessarily a best case, but something very close to a base case, which again would be that the input array is close to sorted, does change the behavior of the algorithm or the expectation of the behavior of the algorithm favorably. So it's interesting to look at the best case as well. Okay? All right, so on with our first elementary sort, which is bubble sort, which you've probably seen it before. I always find bubble sort interesting because if you told me, like if I didn't know any sorting algorithm and you told me like write code, so implement an algorithm and write the code to sort an array of integers, and I didn't know any approach to sorting, I would never come up with bubble sort. I really don't know who came up with bubble sort. It kind of does make sense once you play around with this algorithm, but it's not intuitive to me. Okay, and it's also one of the worst performing sorts. So it's kind of like somebody worked really hard to come up with bubble sort. Okay, so basically the way that this would work, which is outlined here in the bullet points, find minimum item or element on first pass by comparing adjacent items and swap item all the way to the left. Right, so this, so line 2, the for loop in line 2 is basically saying for each item in the array, and then lines 3 to 5 just say like, all right, I'm basically going to bubble down the element that should be in the first position or the current position, reference to code in the ith position of the array. Okay, that's basically what it's doing. Notice that the inner loop, as opposed to the outer loop, goes from right to left. Right, so the outer loop goes left to right. The inner loop goes right to left. Okay, and then basically just comparing the ith element to the one, the jth element to the one that comes, where j is the index of the interior loop. And it's just comparing the element right next to it because it's j minus 1. And if indeed it's lower, then I would swap, right? And so rinse, repeat, right? The first iteration is going to put the smallest element in the first slot in the array. And then the second iteration of the outer loop, after it's done with all the inner loop iterations, is going to place the second smallest element into the second spot in the array, so on and so forth, right? So let's look at how this works. Suppose the input, here's the same algorithm. Suppose the input is right here, 4, 2, 5, 1, and 3. That means that on the first pass, it would pick, it doesn't specifically pick it, but it does so by way of the swaps that you have in that inner loop. It will take the 1 and move it to the left all the way down to the first position. Okay. So then this is pass 2, and this is, by pass here, is pass of the outer loop, right? So, outer loop. Pass 1, place it there. Pass 2 will basically see the 2 and swap it as in the second position right here. Okay. Then pass 3. Okay. Pass 4. And then at that point it's sorted, but if you go with the algorithm step by step, excuse me. So at pass 3, the algorithm is already sorted. But you see that the algorithm would not be able to tell that that's the case, and it will have to run through the fourth pass to figure out that it's moved everything in its place. Okay, so you can see that this last pass is always going to be quite wasteful. It always has to invest one last iteration of the outer loop to determine that there's nothing else that needs swapping down, okay, or swapping to the left. Okay, so this is a non-adaptive bubble sort. Well, how can you fine tune it? We just talked about that, right? How about that last pass? If I can avoid it by somehow detecting that I no longer need to do any more passes, then I can do that, right? I can just break out of my outer loop and I'd be done. So all I need is kind of this Boolean flag that just says whether during the execution of the inner loop, I've actually done a swap, right? So if I've done a swap, then there's nothing I can do. If I've done at least one swap, there's nothing I can do. I still need to go to the next pass, okay? But if I spent that one pass but never end up swapping anything, which would mean that the swapped Boolean would stay false, then I'm really done and I can just break. And then, that's a more adaptive bubble sort, right? Because it's basically with this Boolean flag is keeping track of the current state, if you will, of the array, right? By just trying to figure out whether in a particular pass we ended up having to update any of the elements in it. Okay, so bubble sort is if you did the math, is actually in the order of n squared over 2, but that means it's O of n squared. Okay. Notice that's in terms of number of comparisons, right? In terms of number of times that I need to compare the elements in the array. In terms of number of swaps, okay, if it were the best case, meaning the input array is already sorted when you pass it to bubble sort, then it'll be really fast, right? in terms of number of swaps. It won't need to do any swaps because it'll always detect that there's nothing to swap, right? The left element is always going to be less than the right element. And so never am I actually going to end up swapping. Okay. Now that doesn't. That still means that you can end up doing roughly O of n squared comparisons. In the adaptive version, we still kind of arrive at an O of n squared for runtime, but if it's almost sorted, or actually, if it's the easiest way to see this, if the input is an already sorted array, right? Then really you just have to spend one pass to figure out that it's already sorted, which is a linear number of comparisons, and then you'd be done. Okay, so it'd be quite fast. And also the number of swaps would be roughly linear time if the array is almost sorted. Okay, and as few as 0 if, again, the input array ends up being already sorted. And I know that you're probably thinking, well, what does it mean that it's almost sorted? We'll get to that, but not quite yet. Just bear with me with the notion of having a somewhat sorted array. Okay, so we'll discuss that in a lot more detail when we go to insertion sort, which insertion sort is, it's kind of the better version of bubble sort. Okay, much better version actually. All right. So advantages is very simple to implement, although I would argue that to me, insertion sort would be way easier to implement. Complete some pre-sorting while searching for smallest key. It is stable, right? And sometimes that's important, depending on the context of where you're using your sorting algorithm. Okay. And then the adaptive version may finish quite quickly if the input is almost sorted. So those are some of the advantages. If you thought that bubble sort is terrible, well, there's some good things about it. Although, again, insertion sort has those same good things, and it's way better. So still, bubble sort is kind of a gimmicky algorithm that we, teach. But we would never, in practice, use bubble sort for anything. Disadvantages is an O of n squared time, and it's quite slower than high performance sorts, right? Or efficient sorts. So that's bubble sort. Let's move on to selection sort, and probably this is where we'll end for today, and then pick up insertion sort on Tuesday. Selection sort, again, going back to, like, if you told me go ahead and implement a sorting algorithm for this array of integers, I think that insertion sort is probably the one that I would come up with, right? Because insertion sort is the closest to, if you're playing cards and you're given like a hand of cards, and you're told, hey, and I do this. I don't know if you do it when you're playing cards, but I sometimes sort the cards that I have in my hand, right? And the way that I do it is I look at my cards left to right, and then say, like, all right, the lowest card that I see in my hand is, I don't know, the 5th one. So I pick the 5th one and put it as my first one. Okay. And then what's the next smallest one? I don't know. It's the 7th card that I have. So I pick that one and put it as my second card in my hand. That's basically selection sort. Okay. So here's the algorithm and the code for it. It's basically, the way to interpret it is like this: for each spot in array. Okay? And all this does right here is find next min value that goes in that slot, and then place value in slot. Basically, that's what it amounts to in pseudocode. Okay? And also you have the bullet points down there But I like kind of the more pseudo-ish explanation of what it does. You see the inner loop, right? Lines 4 to, well, it needs to include line 3. So lines 3 to 6, it's just a min function that just searches over the portion of the array that still contains unsorted elements, right? So that's why if you see the inner loop starts at j, where j is I plus 1, right? And then I is the current index of the outer loop. Okay, so that's what it amounts to. So let's look at the example, right, with the same code. Let's say the input is right here, right? Then we have pass 1. What it will do is like, oh, from this entire array, find the min, which is 1, and then place it in that first spot in the array. Then pass 2 is going to say, all right, now I'm going to find the min from here to here. And that min is 2. So that's where I'm going to place it next. And then now the next pass will look at this part of the array, determine that the min is 3. And so it will be placed here. Rinse and repeat until it's done. Okay, so that's selection sort. It's, to me, the most intuitive sort, to be honest. And it has room for improvement. You can actually make it adaptive. By way of, hey, you don't need to invest extra comparisons if I determine that I haven't found an element on the unsorted section of the array that is lower than the current element, right? I don't need to do any swaps, so I just specifically avoid it, right? So if the min index that I found is different than the current slot that I'm at, then that's when I would swap. Otherwise, I don't swap. I basically have the min in its rightful position. Okay? So what does that mean? It means that it is quite adaptive in that, in the worst case, is quite sensitive to input, right? If the array is almost sorted, it means you end up doing almost 0 swaps, right? That's the adaptive version. Okay, which is good, right? But still, in terms of number of comparisons, you have nested for loops where, in the worst case, right, it's gonna, outer loop gonna iterate n times, inner loop's gonna iterate n times, so you have O of n squared. Okay, if you care about doing the actual math, it's roughly around n squared divided by 2. But again, asymptotics, we just care about O of n squared. Okay, so that is selection sort. One particular advantage of selection sort is that there's minimal copying of items, right? You only move or swap things. Okay, well, actually, there is a distinction between moving and swapping that we'll get to when we do insertion sort. But in terms of the copying of items that would be needed with each swap, right? Because it minimizes the number of swaps that it needs to do, again, if the element happens to be in its correct position in relative to the rest of the elements in the array, I don't move it, right? I don't ever move it. That's not necessarily true with bubble sort or even some of the other sorts. In fact, it's almost never true for the efficient sorts, right? You oftentimes, even though elements might be in their correct position in the input, during the efficient sort algorithms, you do end up moving them about just by nature of the algorithms. But for something like selection sort, you wouldn't. Okay, so it is fairly efficient for small n. Okay, and this will be a running theme also for insertion sort, right? That when the array is small enough, you'd rather do one of these elementary sorts rather than using some of the efficient sorts, and we'll talk about why. But just So you start thinking about it. Just because they're much simpler than the efficient sorts, if the array is small enough, you'd rather use a very simple sorting algorithm rather than the more beefy, efficient ones, right? So some of the disadvantages are that it is basically O of n squared. In fact, it is theta n squared, right? It means if you look at the loop, it's a tight bound on n squared. Runtime, it really only slightly changes if the input is pre-ordered, but it does, right? And that's better than bubble sort for sure. It runs about the same if it's already sorted array with all keys are equal or randomly arranged array. But if it's almost sorted, it does run a little bit better. But the one that shines when it's almost sorted will be insertion sort. That insertion sort does behave dramatically better if it's almost sorted. All right, and it's not a stable sorting algorithm. Okay, so that's particularly important. Cool. Actually, let me ask this question, and we'll probably end with this. Why is selection sort not stable? And let's see if anybody want to answer why is selection sort not stable? And you can figure this out by looking at the code. And I'll give it a minute, see if anyone has an answer. Because it is swapping things. No, not. It has to do with swapping. Well, actually, no. Does not have to do with swapping. In fact, it does have to do with kind of the code that decides when it will swap, which is basically that min function. All right, so let's just go over it because, exercises with these like YouTube lectures are not very fictitious. All right, let's go to the this min function right here, which is I call it a min function, but it's just because really these statements, all they're doing is computing the next min that should go in that slot, right? If two elements are equal, correct. I think Varun just alluded to this. Yep, it depends on the implementation of the find min part that are lines 4, 5, and 6, right? If two elements are both the minimum, there's no assurance, right, that the one that was to the left will come out in that same order. It just depends on what that min function sees first. That's the one that's going to move to that position, right? Let's see. If there are two elements with the same key, the second one would be selected as the minimum, so the order of equal keyed elements would be flipped. Yep, that's exactly correct. Elliot, thank you. All right, so that's why selection sort would not be stable. All right, so so far we've discussed bubble sort and selection sort, which are both O of n squared. The next one that we'll discuss is insertion sort, which is also asymptotically slow, but there are a ton more opportunities for tuning to the point where there are situations in which you'd want to use insertion sort. Okay, in fact, at one of our earlier lectures, you heard me allude to intro sort, which is short for introspective sort, which is what STL really uses behind the scenes of their sort algorithm. It basically has, and we'll go over it in more details later, but basically it just picks which sorting algorithm to use behind the scenes. That's why it's called intro sort. And one of the things that it checks is whether the array is small enough or is almost sorted, And if that's the case, it actually uses insertion sort rather than quick sort. Okay, so that's an example of how useful insertion sort can be. Okay, so I'll just show you a brief glance of the insertion sort code, and of course we'll continue in the next lecture. That's insertion sort. You look at it, it's quite similar to bubble sort. Okay, except that I believe the outer loop is exactly the same. I think so, yes. But if not, it's very close to being the same. Like maybe the indexing is a little bit different, but the big difference here is the inner for loop, right? This one goes. Notice that this one iterates over the part of the array that's already sorted. Okay, bubble sort, that inner loop would iterate over the portion of the array that was not sorted. Okay, in insertion sort, the inner loop's iterating over the part of the array that's already sorted. Okay, so at all times with insertion sort, you'll have the portion of the array that's sorted, portion of the array that's not sorted, and all it's going to be doing is look at the next element or the leftmost element in the unsorted section, and then swap it or bubble it down to its rightful position in the already sorted section of the array. Okay, that's what it's doing. So that goes to move items one at a time from unsorted to sorted, inserting each into its proper place. Okay, so at every iteration, the sorted section grows by 1, the unsorted section decreases by 1, right? Because I've moved one of the elements from the unsorted section into the sorted section in its proper place. Okay. This current version that you have in the slides is non-adaptive, and this is where we'll start on Tuesday. I will start with adaptive versions of insertion sort. That's all for today. I think we're finished right on time. I'm glad we covered at least the beginning of insertion sort. All right, remember, project 2 is out. I've had folks in office hours, so it seems folks are starting early, which is good, right? Always refer to the lecture on heaps. It'll help you a lot for implementing the binary heap, basically because we give you all the code. You just need to adapt it to the syntax for the project. Okay, but the concepts are all there. Okay. And then, of course, you have Sith versus Jedi. So, that's great whenever you have. We tried to fit a reference to Grogu and the Mandalorian, but we couldn't do that. We just left it at Jedi and Sith. Okay. All right. Catch you all Tuesday. Have a great weekend. Stay warm. It's really cold in my basement, even though I have a space heater right next to me. If you're in Texas, then hope everything gets better soon. I know it's tough. All right. Take care. Have a great evening and weekend, everyone.